Hi everyone, welcome to this video entitled Current Mode Push-Pull DC-DC Converter using the UC1846 Housekeeping Chores. This is the third video in this series. Previously we have seen this video Qspice number 6 Current Mode Push-Pull Converter using the UC1846 and Qspice number 7, in which we did the implementation of the closed loop circuitry for the current mode push-pull converter. So in this video we are going to finish everything by presenting the soft start implementation. We will also show the load step test, the line step test, the compensation ramp implementation, and finally the auxiliary power supply design. These are other relevant videos related to current mode control, power electronics number 50 and 51, power electronics number 37, and Qspice number 25. So if you are interested in this topic, please take a look at these videos. As we have seen in this previous video, Qspice number 6, we can limit the peak current through the switches by controlling the voltage at this point here at pin number 1. We have selected here a value in steady state of 4 volts, so this resistor here is 1K, this one other here is 4K, so this approximately is 4 volts at this point, and with this, using this expression, we can limit the peak current through the switches to this value, 2.67 amperes. Now, in order to implement the soft start, what we do, as we have seen also in this previous video, is to place this capacitor in parallel with the resistance. So this voltage here is going to increase slowly when we apply voltage to the circuit. In this case, we have selected a value of 470 nanofarads for this capacitor. So the time constant that we have for this voltage here, that is going to increase exponentially, can be calculated with this expression. Rp is the parallel resistance of these two resistors here, R6 and R7. So the time constant is approximately 0.38 milliseconds. So we will reach steady state operation at this point here at approximately 1.1 milliseconds, which seems good in order to implement the soft start process. So here we have our circuit. Let's start by doing a simulation without soft start circuit. So here we are not stuffing this capacitor into the circuit. So this is like an open circuit. And we are going to represent the output voltage, the voltage at pin 1, this voltage here at this point, and the voltage Escent, which is the voltage here at this point, is the voltage here across the sensing resistor, but once it's filtered by this high frequency filter to remove the switching spike. So let's run the simulation and see these results. So here we have the simulation running, and we can see that the voltage I limit reaches approximately 4 volts very quickly, because remember that what we have here at this point, pin 2, is not 5 volts exactly, it's 5.1 volts, but anyway, this is something like 4 volts. This is the output voltage, so we can see that it's high at the beginning and then it's reaching a steady state of 5 volts. And this is the voltage here at the sensing resistor. So we can see that this voltage reaches almost 800 millivolts. So because this sensing resistor is 0.5 ohms, the peak current that we are going to have here is something like 1.6 amperes. We are not using soft start right now. If we do a zoom here, we can see how it's starting. Even we can see some subharmonic oscillations. This is because the voltage at the output is high, so the effective duty cycle is higher than 0.5, and then we have some subharmonic oscillations. And now let's see what happens when we include the capacitor in our simulation. So we click here and then we run the simulation again. So here we see how the voltage I limit at pin 1 is increasing slowly. So the peak current that we have here, the higher value of the current, is around 400 millivolts. So this means it's something like 0.8 amperes. The peak of the voltage is also smaller, and we are reaching a steady state in a much more smooth way. We can do a zoom here, and we can see that we have a much softer start for our converter. And now, to continue with the testing, we are going to do step transient at the load. So here we have included this circuit with a switch and a load resistance of 10 ohms. So we will start with a load resistance of 10 ohms here, and at a given instant with this voltage source we are going to close the switch and connect this other resistance in parallel. So we will have 5 ohms when we close the switch. This is the description for this voltage source. It's a pulse of 5 volts that is going to occur at 1 millisecond. We will simulate the converter up to 3 milliseconds, and then this voltage source, this pulse, is going to go down after another millisecond. So we will see both transient. So let's run the simulation now. And here we have the results of our simulation. So we can see again that we are doing a soft start as in the previous simulation, and at this point here we are doing the connection of the switch. So the voltage at the output decreases at the beginning but then reaches steady state again very quickly. We get 5 volts, and then at this point the switch is again disconnected, so the voltage increases a little bit and then reaches again steady state. Maybe here we can represent this voltage, so maybe even if we multiply this by 0.5 to see everything better. Here we are connecting the load in parallel, and then here we are disconnecting it. We can also, maybe if we like, take a look at the output of the compensator. So it's this pin, so we can see here, or maybe we can move this here. So this is the output of our compensator to do the regulation of the output voltage. And now we're going to do a line step transient. So we have added here this pulse voltage source. So we are going to increase the input voltage from 24 volts in 5 volts, so up to 29 volts at the instant 1 millisecond. And after another millisecond, we are going to go back to 24 volts. And we are going to see the output voltage, the DC voltage here at this point, and the sense voltage here, the voltage corresponding to the sensing resistor. And here we have the simulation running. This is the DC voltage at the input. So we start with 24 volts, then go to 29 volts and go back to 24 volts. And we can see that the output voltage almost remains constant during the transient. And this is so because what we have here is a current mode controlled converter. So it's the inner loop, the one that is controlling the voltage in this situation, because with the inner loop we are fixing the current that we are injecting into the filter that we have here and then into the load, and this peak current is not changing when the input voltage changes, because the output voltage remains constant. Then the output of the compensator is going to remain constant. If we look at the output of the compensator here, we can see that the output of the compensator is not influenced by the input voltage. In fact, we can operate our converter without feedback of the output voltage and by fixing, of course, the peak current that we are injecting at the end at this output, the peak current that is circulating through the inductor, the output voltage is going to be regulated. So it's the inner loop the one that is regulating the output voltage when the input voltage is changing. But now let's see what happens if we increase the pulse here. Instead of going to 5 volts up, we are going to do something like 8 volts down, and then run the simulation again. So now it's running the simulation. We are in 24 volts. Now we are decreasing the voltage at this point, as we can see, up to something or down to something like 16 volts, and then go back to the previous situation. But we can see how now we have some strange ripple here at the output voltage, and then also here is something is happening in the current that we are sensing through the switches. If we do a zoom around here, we can see that we are having subharmonic oscillations, and this is due to the fact that when we decrease the input voltage to 16 volts, the system requires a higher value of the duty cycle, higher than 0.5. So as we have seen in previous videos, when we reach this value of 0.5 and go beyond the duty cycle of 0.5, we will start having subharmonic oscillations. Is what is happening here at this low input voltage. So now what we need to do is to inject an auxiliary ramp to compensate the oscillations and to make our system stable again. So we are going to see now how to do this. In these previous videos, Power Electronics number 50 and 51, we saw that we need an auxiliary ramp to make our converter stable when a duty cycle higher than 0.5 is required by the operation of the converter. And we saw also that we can do this with this circuit here in blue. What we are doing is to take part of the ramp that we have in our integrated circuits, and using this bipolar transistor, we are adding part of this ramp to the signal that comes from the sensing resistor of the switch here. So the equivalent circuit that we have here is something like this. On one side, we have the voltage that we are sensing at this point. We have the series resistance corresponding to the filter RF. And then on the other side, we have the ramp, which is going to appear here, but with something like 0.7 volts less due to the voltage drop between the base and the emitter of the transistor. And then with this other resistor here, we are adding this both together at this point, which is the voltage that we are going to use to do the comparison inside the integrated circuit. So the voltage that we have at this point and at this point at the end is calculated with this expression. So now what we need to do is to calculate these two factors in order to have the correct amount of slopes to make our system stable. The first thing that we need to do is to calculate the slope n prime in order to know the amount of slope that we need to add. But because we are operating from the primary, we have to transform this value into the primary side. So here is n prime from the secondary side is the output voltage divided by the inductance here of the filter. So we need to go to the primary side. So we need to do the conversion as shown here, and we get this value. And by substituting, we get finally this value for this slope. But this is the current slope because we are measuring the current through this sense resistor. We need to convert this slope into a voltage waveform slope. So we only need to multiply by 0. ohms, which is the value of the sense resistor. So we have here the slope coming out of the sensing resistor. And then we have seen in these previous videos, Power Electronics number 50 and 51, that we need an auxiliary ramp with a slope that has to be higher than this value, 1/2, half of the slope n prime. So this is the condition that we need to fulfill. So here is how we are going to do it. as we can see, we are going to take the ramp using this transistor here to add through the resistance RA another voltage to the sensing voltage, and the transistor is supplied from the reference voltage of 5 volts. So if we measure the ramp that we have here, we will obtain this evolution, this waveform. So from this waveform we can get the ramp that we have available here at pin 8, and we have this value. This is the value of the ramp M prime from the primary and transformed into volts per second, and we have to fulfill this condition as we have seen. But now, because of the adder that we have here, we are multiplying the ramp coming from the sensing resistor here by this factor, and the ramp coming from the ramp of the integrated circuit by this factor Kf. So to fulfill this condition here, we have to have this other condition, is Kf times the ramp coming from the integrated circuit has to be greater than 1/2 times the ramp that we are adding here, which is 1 minus Kf times the ramp M prime. So from this condition we can operate, substitute the values, and finally we get that Kf has to be greater than this value that we can approximate to 0.04. And from this, because we have selected here 1K for RF, we can obtain the value of RA equal to 24 kiloohms, which is the value that we have to add here in series with the transistor. But now we can ask ourselves what happens with the DC voltage that we have also in the ramp, because here, as we can see, we have a DC voltage that is something like 2 volts. So this DC voltage is going to be included into the adder. But in this case, first we have that this voltage are going to be transformed at this point into something like 1.3 volts because of the DC voltage drop that we have here between the base and the emitter of the transistor. So we have something like 1.3 volts here DC, and this is going to be multiplied by a very small value, which is 0.04. So the DC voltage that we are injecting is almost negligible. If we want to have more accuracy, maybe we can add a diode or a Schottky diode here in series with the resistance, so we can increase the DC voltage drop, and then we have even inject a lower value of the DC level into the adder. But in any case, we can see that even doing like this, the DC level is negligible, and we will see that everything is going to operate correctly. So here we have the implementation. It's very simple. We only have to add the transistor here, and then the resistance of 24 kiloohms. So we have done a lot of calculations, but at the end the circuit is very simple. So let's run the simulation now and see if everything is correct. So here we have the simulation running. This is the input voltage, now 24 volts. Now it's going down up to 16 volts and then going up again. And we can see that the voltage is keeping almost constant. We have no oscillations at the output. We have some small transient, but very little. If we do a zoom here, we can see that we don't have subharmonic oscillations. The duty cycle here is clearly lower than 0.5, and here is clearly higher than 0.5. So everything is working well. Maybe we can take a look here in the middle, so we can see that the compensation ramp is operating correctly. So let's finally see how to implement the auxiliary power supply. We are going to use this circuit using a series resistor, a Zener diode of 15 volts, and a capacitor in parallel to supply our circuit. So in order to design the power supply, we need to know the current that is going to be absorbed. If we go to the data sheet of the integrated circuit, we can see that the maximum current that is going to be absorbed is around 20 milliamperes. But then we need to know the current that is going to be absorbed by the driving circuit. We can calculate this current from the power that is necessary to drive each switch. So the power to drive the switches is going to be the addition of both powers, and these powers can be calculated with this expression, the voltage times the gate charge times the switching frequency. The gate charge can be obtained from the data sheet of the switches. We have estimated here 20 nanocoulombs for these charges. And the switching frequency is 50 kHz. Remember that the switches operate at 50 kHz, even though the ramp that we are generating is at 100 kHz, because one switch is operating every 20 microseconds. So by doing this calculation, we get this power around 30 milliwatts, and dividing by the voltage, we get finally something like 2 milliamperes being absorbed by the driving circuit. So we need like 22 milliamperes here. We can overestimate a little bit, something like 25 milliamperes, and then we calculate the value of the series resistance here for the minimum value of the voltage, because for this minimum value we need that the zener is still operating in zener zone. So we calculate the resistance using this expression and we get 120 ohms. And then the worst case for this resistance is when we are applying the maximum voltage here at the circuit, and we get that the losses in this resistance are going to be something like 1.4 watts. And here we have the final circuit. We are supplying everything from the input voltage of the converter. So we are using the series resistor here. We are modeling the zener and diode using this ideal diode and a voltage source of 15 volts. And we are using here in parallel a capacitor of 1 microfarad. With this we have a time constant of 120 times 1 micro, so it's 120 microseconds, which is much smaller than the time constant that we have here for the soft start circuit, because we want this circuit, the supply circuit, to be much faster. So it is first supplied the circuit, and then we have the operation of the soft start circuitry. So let's run the simulation and see what happens. Here we have the simulation running. This is the input voltage, 24 volts. We are even here decreasing the voltage, in this case down to 18 volts. So we can see that the output voltage is okay, with 5 volts and is well regulated. Maybe we can add another window and see the voltage here that we have to supply our integrated circuit. So we can see that at this point with 24 volts is okay. We have 15 volts here, but when we decrease the voltage to 18 volts, then we have some decrease in the supply voltage. So something like here we have something like 13.5 volts. So this means that our zener diode is not conducting, and this is because we are having more consumption of current than expected. So to investigate this, I have added these voltage sources here of 0 volts to use them as a current sensor. So let's see what is happening here. We are going to add another window and see, for example, the current that is absorbed by the driving circuit here at pin 13. So we click here, and this is the current that is entering. So if we do a zoom here and we calculate the average, then we can see that the current that is being absorbed by the driving circuit is something like 2.4 milliamperes, very similar to the value of 2 milliamperes that we have calculated. So the problem must be in the current that is being absorbed by pin 15. So let's see this current. We are going to add another window and see this current here. So we can see that the current is much higher than 20 milliamperes that we have estimated for our integrated circuit. So this is something that we have to adjust experimentally when designing the final circuit at the laboratory, because maybe the model of this circuit is not modeling perfectly well the consumption of the integrated circuit. So let's do a fit here. So we can see that the current here is something like 40 milliamperes, so is well above 20 milliamperes that we are estimating. But in any case, the voltage that we are having here is not so bad, so is something like 13.4 volts, so it can be okay to drive the switches. But if we want to have a better voltage here, we can of course decrease this resistance. Maybe we can use 80 ohms. Of course, we are going to have more dissipation on the resistance, but with this we will be able to keep a higher voltage here in the supply voltage. So now we can see that in this part here, the voltage is almost 15 volts. It's something like 14.6, so it's quite good. But in any case, of course, these type of things are issues that we need to solve experimentally when developing the final prototype at the laboratory. Well, this is the end of this presentation. I hope that you find this video useful. Please let me know if you have any comment or question. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.